Good afternoon, everyone. Thank you so much for joining us. My name is Katie Rowley. I'm a librarian at the NOAA Central Library, and we are hosting today's NOAA Innovators Talk. And we are excited to bring this to you today. First, logistics. If you are having trouble hearing and or seeing your screen, the best bet is to log off of GoToWebinar and log back in. That solves most issues. If you're still having issues, you can email library.seminars@noaa.gov, and I will be monitoring that for issues. If you would like to ask a question, please put that in the question panel. We will be answering those at the end of the seminar, and just know that this seminar is being recorded. And with that, I'm going to turn it over to Tiffany House.
Thanks, Katie. Hello, my name is Tiffany House, and I am the NOAA Small Business Innovation Research Commercialization Specialist. The SBIR program provides small businesses with equity-free funding to conduct research and development work that will lead to the commercialization of innovative products and services. Sunburst Sensors received a NOAA SBIR award in 2007. That technology, which will be highlighted today, is available for Phase 3, which means it can be acquired through a relatively easy process as a sole source procurement for NOAA or other federal agencies. Sunburst Sensors is a small company that has done big things in its 20-year history. Its instruments are used around the world to study ocean acidification and the marine carbonate system. Winners of the Wendy, Schmidt, Ocean Health XPRIZE, Sunburst Sensors continues to develop new products to help scientists understand important ocean processes. Sunburst Sensors utilize the funding available through the SBIR program to help innovate. Its sensors are being used under the ice in the Arctic and in the shallows of the reefs of Mauritius. For those of you who are like me and never heard of Mauritius, it is a really beautiful country in East Africa. James Beck is the CEO of Sunburst Sensors and is the chief engineer. For the last 15 years, he has worked with co-owner Mike de Grand Prix on the development of PHP, CO2, and alkalinity sensors for marine and freshwater applications, while building the company into a competitive player in the biogeochemical instrumentation market. He has his BSME from MIT and MSME from the University of Washington. With that, I ask that you give your full attention to Mr. Beck.
Thank you, Tiffany and Katie. It's good to be here today. I am in Missoula, Montana. I'm actually at home today. Hopefully it's a little quieter here and easier to do this. And we'll get through this without any technical issues. We'll see. It's a little weird just talking to my computer, but I hope you can all hear me, and so somebody will notify me if that's not the case, if I'm hard to understand or otherwise. So, Sunburst Sensors, we're helping our customers measure change in the world's water. We have a strong history of commercializing technology, and we're dedicated to helping researchers around the world. And as I mentioned, we're located in Missoula, Montana, a little over 480 miles from the ocean. If you drive on I-90 out to Ballard, go down to the beach there, that's about as the closest ocean water to us. And that's somewhat of an issue at times, but for the most part, it really hasn't caused us any trouble. So we were founded in 1999 by co-owner Mike de Grand Prix. He had developed an instrument called the Isami CO2, meant to measure carbon dioxide at the Woods Hole Oceanographic Institute in the mid-90s. And he and his company had been selling the instrument for about 5 or 6 years when I joined in 2005, by virtue of us working together to get a National Oceanographic Partnership Program grant. That went through the University of Montana, but had a cutout to help Sunburst in terms of doing some instrument development. Along the way, we've used the NOAA SBIR program, NOPP, some NSF grant funding, some funding through the state of Montana, and all those things have helped us, grow and develop our business through the years. In 2011, we were selected for the OOI. I'm going to move this thing out of the way. Hold on. There we go. We were selected by OOI for both pH and CO2 sensors. We've participated in the ACT program with both our CO2 and pH sensors. In 2015, we were winners of the Wendy Schmidt Ocean Health XPRIZE, and I'll discuss that at length later on. Currently, we're at 8 employees, and as I mentioned, a good distance from the ocean. Oops, why is my, oh, there we go, sorry. Some of our marquee customers, NOAA, of course, PML and AOML, Ocean Observatory Initiative, as I mentioned. The EPA, USGS, NASA has bought a Super CO2, Scripps, Hui, Bari, and then worldwide, Alfred Wegener Institute has bought quite a few of our instruments, along with some of the polar institutes. We just had an order from the Norwegian Polar Institute. So we're shipping our instruments, to almost every continent. And, for a business in Montana, it's I think, a real achievement. So going back to the history here a bit, as I mentioned, we used the National Oceanographic Partnership Program from 2005 to 2007. That's when I joined the company, 2005, to bring the Isami CO2 instrument up to date. At the time when I came on board, it was had 4 circuit boards that were hand built, used 18 D cells, a white light source, and just about every one of them was sort of an artisanal work that went out the door a little different from the one prior. And so a lot of my effort was to kind of consolidate and simplify the design down to a single circuit board, away from the white light source to LEDs, and a number of other things that made it a lot easier to produce consistently over time. And what is it that we measure? We're looking at the inorganic carbon system. And in the ocean, that is basically driven by the partial pressure of CO2 in the air, dissolving into the water, where it forms carbonic acid. So the 4 main components of the inorganic carbon system are the partial pressure of CO2, dissolving into the ocean, measured in microatmospheres, pH, which is just a measure of acidity, total alkalinity, and total CO2. Now, if you measure 2 of these items, you can figure out the other 2. So if you use our system to measure pH and CO2, you can calculate the alkalinity and DIC. So one of the reasons people are interested in ocean acidification is that anthropogenic CO2 has been dissolving into the ocean here since the Industrial Revolution, basically. And up top, you can see the Keeling curve, which I imagine a lot of you have seen, showing the increase in CO2. At the time I made this chart, it was 2008, and we were still down under 400. We're well over 400 now, around 415, I believe. And you can see a corresponding decrease in the Hawaiian Ocean time series of the pH. Now it's a small number there, but it's a logarithmic scale, and it represents a significant change in the environment. Since the Industrial Revolution, it's estimated that on the order of 120 petagrams have dissolved into the ocean, and have been released and 40% of that has gone into the ocean. And why is that important? Well, ocean acidification affects calcifying organisms, among other things. It affects the saturation state of aragonite and calcite. Clams, coccolithophores, coral reefs, they all use aragonite and calcite to form their shells. And those are important parts of the food chain, and they're important, in just the web of life. So here are the instruments that we currently make. We make what is called the I and pi and regular SAMI pH, SAMI CO2, SAMI alkalinity. And SAMI in this case, I should mention, stands for Submersible Autonomous Moored Instrument. We also make the AFT pH and AFT CO2. Those are autonomous flow-through instruments used on shipboard applications primarily, or some people are using them on the bench to do bottle samples. And then finally, we make a super CO2 instrument that uses NDIR to measure CO2. So talking about the SAMI and AFT instruments, they're low power, allowing a long deployment. They have low to no drift. They log and transmit the data serially, RS-232. They can support up to 3 external instruments. The SAMI instruments are rated to 600 meters depth, and they've been designed for commonality and consistency. So if you use one of these instruments, you can use almost any of them. They all use the same client software, and they're all based on some common principles. Now I'm going to discuss briefly the Super CO2, which is an instrument developed with SBIR funding, and it's a different animal than most of our instruments. As Tiffany mentioned, we had SBIR phase 1 and 2 in 2007 to 2009. And during that time, we developed the Super CO2. It's for shipboard or benchtop use. It uses non-dispersive infrared, a Lycor 850A in this case. It equilibrates a stream of water through a contactor or shower head, shown here on the left and right, the contactor and the shower head. You can use up to 4 gas standards with this instrument. It will support thermosalinograph, GPS system, and other instruments if the customer requires. It provides real-time data at a high sampling rate, up to 1 hertz if you need it. And it's tablet driven, so it's all self-contained right there. What you see on top is the tablet with the PC system running the software that drives the whole system. So you can kind of carry this on board your ship, strap it down, plumb it in, and take it on a cruise. So it's a nice system in that regard, in that it's portable versus a lot of other instruments of this type that are actually required. They get built into the ship and are considerably more expensive. Also, during that SBIR phase 1 and 2, we developed the autonomous flow-through instruments, pH and CO2. Again, they're used for shipboard or benchtop measurements. They use the same software as the SAMI instruments. They're externally powered, require a flow rate of 2 to 4 liters per minute. One nice thing is you can set it, forget it. You can plumb it in, start it, and walk away. And one illustration of that is that we installed this on a boat shown there in the lower right on the Clipper race around the world. On the left, that's me installing it. We ended up having to install it in the lavatory above the door because that was the only space we could really find that was unused in that ship. But it worked well, collected data as this ship did a transit down the west coast through the Panama Canal, excuse me, and up the east coast to New York. Tiffany didn't mention, but I will, that we also received a second SBIR phase 1 and 2 in 2013 to 2015. And during that, we developed what is now called the Isami, and then later spun off the Pisami. The aim there was to reduce the size of our instrument for drifters, and this development effort coincided with the XPRIZE, which I'll discuss here in a minute. The Isami won the affordability purse. It's for use near the surface, just 3 meters depth. And our follow-up instrument, built around the same ideas, the Pisami, goes to 100 meters. So it's sort of halfway between our full-blown regular SAMI pH and the Isami. So this is just a picture of the actual units that went into the XPRIZE. We had to make 3 of each. On the left is the titanium T-SAMI. We entered that in the accuracy purse. We needed the titanium housing because we were going to 3,000 meters. And on the right is the Isami, I for inexpensive in this case. And we entered that into the affordability purse. It looks quite a bit different there in the early beta stage. It was basically just a PVC tube and trying to make it as inexpensive as possible. We actually built the whole thing for under $1,000 in terms of materials. Excuse me. So following the XPRIZE, excuse me. The Isami pH has been used by the Ocean Foundation and their Ocean Acidification Initiative, and they're providing training to scientists in developing nations around the world. The Isami pH is part of their Ocean Acidification Monitor Kit. They're building capacity and providing valuable data sorry, for use by researchers on the topic of global ocean acidification. They've held workshops in Mauritius, Fiji, and Central America. There's some pictures here showing some fellows down on the left in Fiji with newer versions of the Isami. Up top was on a visit to Mauritius with an earlier prototype of the Isami. And in the bottom, I'm pictured with some of the participants in the workshop in Mauritius. And Mauritius is just about as far as you can get from Montana, at about 10,000 miles out in the ocean, excuse me, east of Mauritius, I'm sorry, east of Madagascar. But it's considered to be part of Africa. Okay, so I'm going to back up and talk a little more about the Wendy Schmidt Ocean Health XPRIZE, which we participated in. As I mentioned, there were 2 purses, the accuracy and affordability purses, and we participated in both. The total prize money was $1 million for each purse. It was approximately 1 year from start to finish. Started out with some bench and tank tests at Mabari, and then moved on to a real world, in quotes, tank test at the Seattle Aquarium. And from there, the accuracy test continued, although the affordability test was done. And that was at Station Aloha in Hawaii. We went out for a 6-day cruise. And it provided us, an opportunity to test our technology against others that are out there doing the same thing. So we participated because we believed in our technology, and it gave us an incentive to pursue new ideas. And it also dovetailed with some work that we were already doing with the SBIR project, which was to make a less expensive, smaller version of our instrument. It gave us a chance to learn. Getting out on research cruises is not cheap. So it was a chance for us to get out and deploy on the ocean on a research vessel, and that was valuable to us. So even if we came away with nothing, we were going to consider it a win. And it helped bring visibility to us and to a problem that we believe is really important. Just some quick numbers. At the outset, there were 77 different teams intending to compete, but only 24 actually registered, and I believe only 16 made it so far as to get into the testing. 8 different countries were represented. There were backgrounds, engineers, oceanographers. There was some people from the food industry. There was a team from a high school in California. There was an instrument that came from an agricultural background. And in terms of technology, colorimetric, we were colorimetric, of course, but there was also the ISFET type, an optode, electrochemical, glass electrode, and then one team from Japan used a hybrid colorimetric electrochemical system. And this is just some sample data of ours taken during the casts on that research cruise as it goes down to 3,000 meters. And as I mentioned, we ended up winning both the accuracy and affordability prizes. And I'm going to try to play this video. We had mixed luck in terms of how well this came across. It's only 4 minutes, so bear with me if it's kind of choppy.
I call myself an inland oceanographer because we don't have an ocean here near Montana.
We are at Sunburst Sensors World Headquarters here in Missoula, Montana. One of the challenges of doing chemical oceanography 480 miles from the ocean is getting seawater. Last time I was in Seattle, I was out there just a family vacation, and I ended up wading out to Puget Sound with this jug. Got my pants all wet. We are part of the Wendy Schmidt Ocean Health XPRIZE. I'm team leader of Sunburst Sensors. Our company was founded in 1999 to study PCO2, which causes ocean acidification.
We have increased CO2 in the atmosphere. It's causing the pH change in the ocean as that carbon dioxide is absorbed.
The oceans are sucking up huge amounts of CO2. And as pH changes, it can disrupt the food chain. That's a very serious thing in a world where a lot of people depend on the sea for food. We developed one of the first CO2 sensors for marine use. 8 years later, we made a sensor specifically for measuring pH. This is where the magic happens. Right here is our manufacturing space. This table is sort of the center of activity. A lot of history here, just in terms of notches and cuts and drill holes. Tiffany mascot dog. Mike and I and Catherine, my wife and bookkeeper for Sunburst, all went to high school together.
We were close friends because we're both science geeks.
He's working at another instrumentation company in Seattle. It's not a gamble. Come back. There was only 2 years of funding. It didn't work out, and there's not a lot of mechanical engineering jobs.
We had 2 children at that point and had decided that we wanted to come home to raise them.
Roll the dice. So it worked out.
The SAMI is a submersible autonomous moored instrument. SAMI pH, which is what we use in XPRIZE, measures pH. We call this one the T-SAMI because it's made of titanium, so it's a titanium SAMI. We call this the I-SAMI because it's inexpensive, so the inexpensive SAMI. What I really like about these is that they're so simple. Software is very easy to use, and you just put the instrument in the water and you let it go and you come back and you have data.
When we first started talking about doing the XPRIZE, I'd already been working on miniaturizing the SAMI-2s and looking for a way to make it more inexpensive so that we could get it on a whole different platforms, not just mooring to booms.
I think it's great to have this competition just to be able to compare, look at all of those instruments that are out there and see how well we're measuring pH.
We're going to learn a lot from this because we couldn't go out on our own and throw a sand down to 3,000 meters and collect it. Pretty excited to see what happens. I mean, right now we've got the T-SAMI, our instrument going down on the rosette, and in about an hour or so we'll find out if it worked. We're a small company, we're trying to do a lot. our approach requires a diversity of talents. I mean, we have to do some electrical engineering, we have to do software, there's fluidics because we've got tiny little pump, tiny little valve, there's mechanical design, pressure housings. For better or worse, we have more moving parts than some of the other approaches. And it all has to work by itself at depths up to 3,000 meters, incredible pressure. Just the tiniest leak will destroy the instrument immediately. It's good when it comes up, you hear it ticking. That means it's working. It hasn't leaked. Let's see what happened there. It's not ticking the key, but it seemed to work.
So that's the first time it came up that ticking.
Yeah, but it downloaded, so it didn't flood. Must have just locked up at the last minute. It's running now. We're a small company, and so we're competing against some teams who have a lot of resources, and we've made a long way. So I mean, that feels good that we've proven that with just a small team that we can do something this big.
Okay, so I apologize if that came through choppy, but if you're interested, you can find it on YouTube by searching Sunburst Sensors, Wendy Schmidt, if you're interested. And so this slide just shows some of the media, media coverage post-prize that we received. The XPRIZE is really good at generating media coverage. I got to go on the Weather Channel with Al Roker very early in the morning, the day after we knew we won. So that was exciting. But there was articles written up in quite a few publications in the popular press, and you can see those here shown. And here's a few more. Got a little something from Popular Mechanics. So going forward, one of the projects we're working on is to try to add our Isami technology to Lagrangian drifters. I've just included a figure of, what is a Lagrangian drifter. It's basically something you throw in the ocean and it is pulled along by the current and sends measurements back via satellite. Right now, they mostly just send back temperature and location, but we think it would be easy to add our technology to also monitor pH as they float along. And so we're working on that right now. We kind of got interrupted with the pandemic. We're hoping to pick it back up and get it moving again here pretty soon. And with that, I guess I've reached the end of the presentation, and I'd be happy to answer any questions anyone has.
Awesome. Thank you so much, James. Okay, we do have a few questions, and if you are typing in the question panel right now, thank you, and I will be answering or asking questions as they come in. So our first question is, are there any researchers currently using the Isami?
Yes, so as I mentioned, the Ocean Foundation people are putting these out in the field with researchers that they're training at locations around the world. I think they have on the order of 20 of them or so. I'm not really sure right off the top of my head. But we've also, I believe, shipped some to the EPA. We've got a couple people doing some coral reef stuff with them. Yeah, I don't have that right in front of me, like who all is using them, but I think we put out at least 30 or 40 of them.
Okay, great. Also, do you have researchers currently using the T-SAMI with the titanium housing?
Well, actually, we have our first T-SAMI customers, and they were going to be deploying in October, but the cruise got pushed out a year because of the pandemic. So we have the instruments just about all built up. There doesn't seem to be a tremendous amount of interest in going much deeper than 600 meters. Seems like 1 or 2 people a year ask about it, but nobody follows up. So it was great to actually get somebody who needed that.
Great, thank you. Our next question. Can these instruments that were developed for ocean use also be deployed in freshwater, such as lakes, to monitor for acidification as well as other water quality parameters?
So yes, CO2 instrument doesn't really care if it's freshwater or marine water. The pH instrument, we use a different reagent because the pH range is typically different in freshwater. It's lower. One problem with pH range in freshwater is sometimes larger than we can measure, but for a moderately buffered system, we can do freshwater.
Great, thank you. Our next question, how long have you deployed these sensors for? How did you deal with calibration and drift over the deployments?
So we don't ourselves deploy too often, but our customers have deployed these, for up to a year or more. The technology we use, which, as I mentioned, is just reagent-based colorimetric. One of the advantages of that approach is that it doesn't really drift. As long as, the main causes of drift are things like biofouling that actually change the microenvironment around the sensor. So that's always an issue for just about any type of instrument. Let's see, did I answer that whole question or was there another part?
No, I believe you answered it. You said for how long, you did mention how long you deployed them, or have you deployed them for?
Right, yeah, so, and one thing, if it's not clear, is that these are designed to be time series instruments. Typically, you're taking measurements every, half hour to an hour, looking at changes over weeks to months. So they're not meant for high frequency monitoring. Except
Great, thank you. Okay, thank you. Our next question. How much IP do you retain in an SBIR process? What rights do you give away to your technology in the SBIR process?
Well, that's a question for the SBIR people, but basically the SBIR program doesn't ask a lot of you. I can't remember the exact terms of the agreement, but basically you have control of your intellectual property for the most part, and it's a great mechanism in that sense versus, say, typical venture type funding. If you could even interest anybody in investing in something as obscure as ocean monitoring, which is unlikely. In that type of funding scenario, you tend to give up some of your intellectual property, as well as some of your ownership of your company.
Okay, thank you. Our next question, how do you manage flow rate with shipboard mountings? For example, if mounted on a relatively fast moving vessel, such as a cruise or merchant vessel?
Well, that's typically up to the customer, but what the flow is typically not generated by the movement of the ship. It's generated by a pump somewhere in the ship. And there's considerations about how to do that in the best possible way. You want to pump the water so that it changes as little as possible by the time it gets to your instrument. But that's kind of nitty-gritty details.
Great, thank you. Our next question, what type of telemetry is being employed for real-time data transmission?
So typically, we don't do that part of it. We have worked with customers. My business partner, co-owner Mike DeGrampri, has instruments under the ice in the Arctic, and they use what's called an inductive modem system to transmit our data up the mooring line to a surface expression, and that in turn is transmitted by satellite. I don't think they may be using Iridium. I'm not sure. I'd have to double check on that. I think that answers the question.
Great, thank you. Okay, our next question. In relatively clear tropical water, 30 to 40 meters in depth, what is the potential deployment length logging at hourly intervals? Is biofouling an issue in these lengthy deployments?
Yeah, as I mentioned, biofouling is always an issue. And that really depends on the environment where you deploy. Ideally, if you can mitigate that or eliminate that, you could deploy a CO2 instrument for a year or more on hourly intervals. The pH instrument could be deployed on the order of, well, it could be deployed a year if you use extra battery. With just a single battery, it could be deployed about 8 months, I believe, right now. It's more limited by power because it pumps more often, whereas the CO2 is reagent limited. But biofouling ultimately limits things a lot more than the instrument itself, or can.
Great, thank you. Our next question. Have you seen growth in the market since winning the XPRIZE? And if so, how much?
Yeah, we have received, I don't really have a good metric on that. I know that it certainly helped get our visibility up. Some people probably gave us a second look who maybe went with a different technology in the past. But I can't say exactly, 20% increase or whatever. It is a niche market. Only so many people out there really need to measure with really high accuracy the pH or CO2 in the ocean. We are working on some other projects for citizen science, a handheld monitor, for instance. But that's a whole different ball of wax. Getting off topic a bit.
Great, thank you so much, James. I am not seeing any more questions, so I'm going to give everyone another 30 seconds or so to type them in. But if we don't have any questions, just a reminder that this was recorded and we will be putting this up on the library's YouTube channel in the next 24 hours. So if you'd like to send this to a colleague, or if you had to step away at any point and would like to rewatch it, you can find it there. And with that, I am not seeing any more questions. Tiffany or Jim, do you have any last comments you'd like to make?
I'd just like to thank everybody for tuning in. If you have any questions, feel free to reach out to me personally, or just to the info@Sunburst Sensors email address. Yeah, and that's it. Thank you all for attending, and thanks to you, Katie and Tiffany.
Thank you, Jim, and same here. If anybody has any questions, they can reach out to me, Tiffany, that house, like the house you live in, at NOAA.gov.
Wonderful. Thank you all, and have a wonderful rest of your Wednesday. And we will see you next time for our next NOAA Innovators, which is going to be next Wednesday, I believe, on September 16th. Thank you all.